Good morning, everyone. Today I will be presenting a computational fluid dynamic simulation on the 50 caliber BMG bullet to understand how different bullet diameter and turbulence model influence aerodynamic performance. For this analysis, CFD simulation were performed using SimFlow under turbulent and incompressible flow condition. So we evaluate three turbulence model, which is K epsilon, K omega, and K omega SST, and also three bullet diameters, which is 20, 26, and 30 mm. So our purpose was to study how this variable affect velocity and pressure around the bullet. So the results show that increasing diameter decreases the velocity and increases the pressure. uh, all of three turbulent model K omega SST provides the most accurate and stable result. The project has two main objectives. The first objective is to analyze how varying bullet diameter influence aerodynamic performance. The second objective is to compare the impact of turbulence model K epsilon, K omega, and K omega SST on maximum velocity and pressure. The 50 caliber BMG bullet is a large caliber, high power bullet used in military application. So it capable of piercing armor and damaging light vehicles due to its massive energy and velocity, with effective range over 1,500 meters. These properties make it an ideal case study for CFD analysis. Okay, several methods were carried out to analyze the aerodynamic performance of the bullet. So the first method is geometric creation. So the bullet geometry was created in SolidWorks and imported into SimFlow as STL file. Next, the meshing generation. So the mesh was structured and the hexahedral mesh is used, and the mesh is consisting of 34,924 elements and 41,598 nodes, providing a good resolution around the bullet. So as you can see in the image, the finer mesh is generated around the bullet body, and coarser mesh is generated at less critical area. So the next step will be solver selection. So we use the simple algorithm for the steady state and incompressible flow simulation. So the next step will be the boundary conditions selection. So the selected boundary conditions are shown in the image here. So the selected boundary conditions are outlet, inlet, top, bottom, bullet body wall, and symmetry. So for the inlet velocity was set to 832 meter per second, matching the real bullet speed. For the next step will be the monitoring. So in monitoring, we create the slices to visualize the flow data at specific plane. So for this analysis, we're going to create a slice to visualize flow data at X and Z plane. So this help observe flow variable like pressure and velocity across the bullet body. So once we create the slide, next we're going to set the number of iteration to 200, so that the solver run for 200 iteration. So once the number is set, then click the play button to run the simulation. So this table show the simulation parameter. So the simulation parameter are bullet diameter and turbulence model. So the bullet diameter consists of 20, 26, and 30 mm, and the turbulent model consists of K epsilon, K omega, and K omega SST for each diameter. So from the table, we can say that the independent variable will be the bullet diameter and turbulent model, and the dependent variable will be the maximum velocity and maximum pressure. After running the simulation, we were able to capture the result of maximum velocity and maximum pressure. For maximum velocity, as you can see in the table, as the diameter of the bullet increases, the velocity in turbulent model for k epsilon is decreases. So this trend is followed for the remaining model. Same goes for the maximum pressure, but in this case, as the diameter increases, the pressure in turbulent model of K epsilon is increases. So this trend is also followed for the remaining turbulent model. From the result table, we were able to illustrate a line graph. So this line graph is maximum velocity versus bullet diameter. So this graph showed a decreasing trend of velocity as the bullet diameter increases. So there are three lines. So the red line is k epsilon, and the blue line is k omega, and the green line is k omega SST. So all of three turbulent model, k omega SST show more stable and accurate prediction of maximum velocity. Same goes for the maximum pressure versus bullet diameter graph. So this graph show increasing trend of maximum pressure as the bullet diameter increases. So all of three turbulence model, KW SST model show more stable and accurate prediction of maximum pressure. So these are the color contour plot of velocity and pressure for bullet diameter of 20 mm. So the turbulent model used is K epsilon. Next, these are the color contour plot of velocity and pressure for the bullet diameter of 26 mm. So the turbulent model used is K omega. And finally, these are the color contour plot of velocity and pressure for the bullet diameter of 30 mm, and the turbulent model used is K omega SS3. So, from the color contour plot, we can say that as the diameter increases, we observe that velocity decreases due to a high air resistance. Meanwhile, pressure increases, especially at the bullet tip, due to greater surface area facing the airflow. This is because the diameter increases. So these trends are visible across all the model. So note that only selected plot are shown in this presentation, but the full set of contour plot result of all turbulent model for each bullet diameter is available in the report. So here we're going to discuss the result in three terms, which is velocity and pressure trends, turbulent model comparison, and percentage of deviation. So for the velocity and pressure trend, as the bullet diameter increases, the velocity decreases while the pressure increases, especially at the nose of the bullet due to the increased impact with the air molecule. So next is the turbulent model comparison. In comparing the model, K epsilon tend to predict higher velocity but less accuracy near walls. K omega capture near wall effect better, and K omega SSD give more most balanced and stable result. So for the percentage deviation, K omega SST model has lowest deviation in both velocity and pressure. So this show that the K omega SST is more stable and suitable for cases with complex flow and boundary separation. So in conclusion, the project objective is achieved. The bullet size and turbulent model significantly affect the performance. Uh, for instance, as you can see in the result, as the diameter increases, the velocity decreases and the pressure increases. And out of all three turbulent model, K omega SST is preferred for accurate velocity and pressure prediction. For future work, we can include a bullet spin and compressible flow, and try LES or DES model for better turbulence accuracy, and run transient simulation to stimulate realistic flow condition. Also, Please note that the technical drawing of the bullets and the residual graph from the simulation are included in the full report for further reference. That's conclude my presentation. Thank you for listening.